webinar series. Today, our speaker is Alejandro Rodríguez. Alejandro is a professor of economics at Universidad del CEMA in Buenos Aires. He's the director of the economics department. He holds a PhD at the University of Chicago, and before being at Universidad del CEMA, he was an assistant professor at State University of New York at Buffalo. And his research interests are on economic growth, monetary policy, and international trade. And today he will be talking about quasi-fiscal deficit financing and hyperinflation. Thank you, Alejandro. The floor is yours.
Right. Thank you, Alberto. Hopefully everybody can hear me fine. Can you hear me now as the Sprint advertisement go a couple of years ago when I was in the US? But let's get started. And well, the topic today is quasi-fiscal deficit financing and inflation and maybe hyperinflation. Okay. So I'm thinking mainly about the case of Argentina back in the late 80s. Probably you all know it, but if you don't, we had very high inflation in the late 80s and early 90s, and I'm going to argue that that had to do with quasi-fiscal deficits. And it's not a novel idea, but I think what I have in this research is another channel through which quasi-fiscal deficit financing might affect inflation. Okay, so Argentina has run fiscal deficits for most of its history, or at least the last 70 years. Deficits were usually financed in part with money printing, which led to inflation. And in the second half of the 80s, well, they were not an exception on terms of fiscal deficits, but turns out that they were not that high compared to the fiscal deficits that we observe in the 1970s or the first half of 1980s. But yet inflation was much higher. Okay, so I'll show you some figures now to get an idea of those numbers. Okay, so here we have the red line is the fiscal deficit. Okay, that includes the primary deficits and the interest payments on the government debt. And the green line is the change in the money supply divided by GDP. Okay, so we can see that obviously Argentina has had deficits for most of its history, maybe a short period in the early 2000s in which we actually had surpluses. But before convertibility in the 1990s, fiscal deficits were financed with money printing. Okay, but the funny thing about these figures that we have here is that if we observe, for example, the fiscal deficit in the second half of the 80s, okay, starting in 85 and finishing in 1990, they were not that high compared to the fiscal deficits which we had in the previous decade. Okay. All right. So questions are welcome at any time. Hopefully, I will notice them, like I noticed Francisco's comment right now. If not, just try again. Keep trying until I notice your question. Okay. But going back to the presentation, if we look at the inflation rate in the second half of the 80s, we will notice that it is a lot higher. Okay, so that's the inflation rate in Argentina in the consumer price index. Okay, so yes, we did have very high inflation in the 1975, 1985 period, but nothing compared to this. Okay, so that's a hyperinflation. Okay, so what was different? So many economists, in particular Almansi and Rodríguez 1993, showed that quasi-fiscal deficits, well, they played a very important role in the Argentine hyperinflations of 1989 and 1990. Okay, in the 80s, the Argentine Central Bank, I'll just call it CB in the presentation, tried to control the money supply in many ways. Okay, it was printing a lot of money because it had to finance the treasury, but also because it was doing a lot of funny stuff. Okay, so giving bad loans to banks, or banks actually were giving bad loans to some industries, and then the central bank had to rescue those banks, and that implied a lot of money printing. But then the central bank tried to sterilize part of that, increasing the money supply. Many instruments. It paid interest on reserves, and it started to issue debt. Okay, but once you start to do that, then you get another source of quasi-fiscal deficit, which is which are the interest on the debt that the central bank has. Okay, interest start to grow as the debt grows, and usually the maturity of that debt starts to shorten. Okay. So I'm going to argue that that debt is actually different from regular financing to the treasury to pay, I don't know, wages or other expenditures, and that's the source of very high inflation. Okay, so this figure here shows the rate or the ratio, I'm sorry, of the monetary base plus central bank debt to monetary base. Okay, so if there's no debt in the central bank, and the only thing that has on the liability side of the balance sheet is the money supply, then that ratio is 1. Okay, so we see in this figure that in the second half of the 80s, okay, the central bank started to issue a lot of debt. Okay, and that debt was actually like 3 times the money supply. I'm sorry, 2 times the money supply. Okay, so the ratio is actually 3 once you add the money supply. Okay, these numbers are just a representation. The real figures should be done with a lot more care, because what we actually care about is the part of the liabilities, or the liabilities in the central bank balance sheet, which pay interest, and those that don't. Okay, usually reserves do not pay interest, but in the 80s they did. So we should actually remove those from the money supply that is dividing the monetary base. Okay? And that would actually make the ratio a lot higher. Okay. If you notice on this figure, there's actually an increase in that debt to monetary base ratio starting in the second half of the 2000s. I'm not gonna talk about that in particular in this paper. There are other issues going on. In particular, once we extend it to the more recent years, starting, I don't know, 2016, 2017. Which are of interest, but I'm not going to get on that issue right now. Okay, so the traditional explanation on why quasi-fiscal deficits can generate a hyperinflation is basically the simple Laffer curve effect. Okay, there's a limit to how much inflation tax can be raised, and trying to go beyond that limit will generate a hyperinflation. And in this paper, we try to show that very high inflation can arise even though there's no Laffer curve effect. Okay, so I'm going to be working with a perfectly inelastic money demand function. Okay, then we also show in this paper, or actually it's a finding that comes out of the simulations that I'm going to show you later on, that in a discrete time version of the model, which I'm going to show you is the version I'm going to show you is the continuous time, but if we think of it as a discrete time version of the model we simulated, we find that the length of the period matters. Okay, so whether the model is calibrated to be, I don't know, a yearly based model, is going to yield a very different result than if we think of it as a monthly model, weekly, daily, or whatever. Okay, so the related literature, okay, so I'm going to be thinking about, I don't know, choosing the optimal inflation rate from the point of view of the central bank. Inflation is a tax, so this has to do with optimal taxation. So, for example, it's somewhat related to the literature started by Lucas and Stoke in 1983. Also, Alvarez, Quijo, and Neumeyer, Persson, and Svensson, and Nicolini in 1998. Okay, so most of this literature focuses on under what conditions is the optimal tax policy time consistent? Okay, I'm going to be working with a model in which there's a time inconsistency issue. Okay, and these papers that I'm showing you here, they focus on, okay, so under what condition is the optimal monetary policy time consistent? Okay, but they don't really worry much about how the time inconsistent policy, how the time consistent policy, which is sometimes not optimal, looks like. Okay, it's going to be somewhat related also to the work by Barrow Gordon. You all know that. And if I had to put it in context, it's very similar to the work of Nicolini in 1998, in the sense that if I had to present a fully optimizing model with a household sector and a benevolent central bank that has to maximize the utility of the agents, it would look like a lot like the Nicolini paper. Okay. So let's get to the model. Okay. At time t, this is going to be the continuous time version of the model. I will not present the discrete time version of the model, but I will present the results. Okay. So at time t, the central bank has nominal liabilities. I'll call them LT, which is basically debt plus monetary base. The true distinction should be made also among interest-paying liabilities and non-interest-bearing liabilities. So here I'm just going to assume that the monetary base pays no interest and debt does pay interest. Okay, so nominal liabilities are debt plus monetary base. The budget constraint from the central bank is given by, well, whatever it has to pay on interest, it has to pay on its debt, IT times DT, plus some potential transfer, let's call it GT, that it has to make to the treasury. And well, those expenditures, they have to be financed by either printing more money and .T or issuing new debt, DT. Here, debt is like a zero coupon bond. Treasury transfers, you can model them as being a constant fraction g, little g of the money supply. I'm going to try to keep things very, very, very simple. Okay, I'm going to assume that the money demand is completely inelastic with respect to the interest rate. Okay, and that it grows at a constant rate alpha. Okay. That's the way I presented in the paper. Actually, in the simulations and the rest of the equations, I'm going to make those alpha and g's equal to 0 so that they don't show up in the presentation, because they really don't add that much. Okay, and we also have a Fisher equation. So the nominal interest rate is the real interest rate plus the expected inflation rate pi et. Okay. So now I'm going to define the state variable for my problem, okay, and that's going to be the real value of nominal liabilities normalized to account for growth in the demand for base money. Okay, so XT is going to be the important variable here. It's the nominal liabilities, which remember it's the central bank debt plus the monetary base. We divide that by the price level and the factor E alpha T, which accounts again for growth in the money demand. Okay, so we do the usual solo type of algebra. Okay, and write the budget constraint for the central bank in terms of XT in real terms. Okay, so let me change to the draw here. So here it's what you have to spend. Okay, so what the central bank has to spend on, what does it have to spend? Well, it has to pay interest on its liabilities. Okay, so oops, that doesn't really show up very good. The liabilities are the total the interest-bearing liabilities are the total liabilities minus the money supply. Okay, you have the nominal interest rate, which is R plus pi ET. Okay, but with inflation, you equate or reduce the real value of those liabilities. So you have the pi t subtracted there, and since money demand is growing, you also get the alpha term there subtracted. Okay, and on the income side for the central bank, well, you get the inflation tax. Okay, and you also, well, there you have the G, which is also part of the expenditure value, showed up there to accommodate it with the M factor. Okay. But as I mentioned before, I'm going to make alpha and G disappear by setting them to 0 so they don't bother in the equations. Okay, so now I'm going to take an approach on the central bank's objective, which is more like Barro Gordon instead of the traditional literature on optimal taxation. And I'm simply going to assume a loss function for the central bank that depends on realized inflation. Okay, so here, what the central bank is, this is going to be important. Okay, what the central bank cares about is realized inflation. Okay, in many models, what you get is that the central bank cares only about expected inflation. So unexpected inflation, if you, I don't know, subject the economy to a burst of unexpected inflation, then that's not going to matter much, because since it was unexpected, then it didn't come up in the expectation of inflation in the previous period, so it didn't affect the nominal interest rate, so it doesn't affect the money demand. Okay, I'm going to work under the assumption that the central bank actually does care about realized inflation, not about expected inflation. There are ways in which you can rationalize this idea. For example, Nicolini in his paper, he works with a cash in advance model in which the previous period in which the cash in advance is determined by the beginning of period money supply, which is what you get from the previous period. So a burst of inflation, even if it is unexpected, will lower the cash holdings in real terms that households have to make purchases, and that would produce a welfare loss. Okay, so that's why I was mentioning to you that I think that the Nicolini paper is actually quite related to this work. Okay, so I have to make some regular assumptions on the parameter values. So, for example, theta, which is the curvature of the loss function with respect to inflation, has to be greater than 1 so that the loss function is convex. And also some parameter values on rho, the discount rate for the central bank, the real interest rate R, and the growth rate in the money demand alpha. Okay, so that the problem is well defined. Okay, so that we don't get infinite utility or the central bank just issuing debt forever. Okay, the real interest rate, I'm gonna take it as given. Okay, so it's going to be another parameter in the model, but we could actually set the interest rate equal to the discount rate R equals rho and go on. Okay, because R equals to rho is what you usually get on models in which you have an endogenous real interest rate. As I mentioned before, to just keep the algebra clean, I'm going to set up alpha, which is the growth rate in the money demand function, and G, which is the transfer for the treasury, equal to 0. And I'm going to work with the particular case in which theta, the curvature, is equal to 2, so you get a quadratic loss function. Okay, that's going to make the algebra a lot simpler. The first assumptions, alpha equals G equals 0, are basically harmless, are trivial to the results. Okay, so obviously if you have to transfer more money to the treasury, you will get more inflation, and if money demand grows faster, well, you get less inflation. No surprise there. Okay, the second one, the second assumption, theta equals to 2, is not trivial, and I'll come back to it later. Okay, so that one does matter for the results. Okay, so now the basic setup of the model is presented. If you have any questions about the setup, now it would be a good moment to make them. Okay, so I'm having some mate right now, the advantages of this webinar series. Okay, so no questions. I'll just go with the description of the 4 solutions that we are going to look for. Okay, one is the solution with commitment. Okay, so the central bank announces a path for inflation that will generate an expectation of inflation, and then the central bank cannot deviate from it. Okay. Obviously, if there's a time consistency issue, then the central bank would like to deviate, and that's actually what would happen. So then that might not be an equilibrium. Of course, it could be an equilibrium if we could find some mechanism under which the central bank can gain reputation and sustain the commitment solution. I'm not going to worry about that. But there's going to be a solution which commitment, okay, which is going to be the first best solution. Then I'm going to present another solution, which I think it might be related to inflation targeting. That's the name I give it, but that's something that could be debated. Maybe there's a better name for it. Okay. So in this solution, the central bank is going to take as given a particular path for expected inflation, and that path is only going to be a function of time. Okay, it's not going to be a function of the evolution of the state variable. Okay, so it's only a function of time. Okay, so this is not really going to be an equilibrium with rational expectations, because if the central bank deviates from this path, then it would want to do something different in the future, but expectations are not going to adjust to that change. Okay, still it's going to be an interesting solution because it's a solution in which the central bank announces a path for inflation. People believe in that path, okay, and then the central bank finds it optimal to keep on that path. Okay, but again, if there's some deviation for some reason, then the path is going to like screw up. It's not going to be an equilibrium then. Okay, but that's also common to many models with inflation targeting, in which off-equilibrium paths are really weird, and that works as a mechanism for selecting the good equilibrium path. Okay. Then I'm going to show you the solution with no commitment, in which the expected inflation rate is going to be a function of the evolution of the state variable, xt. Okay, this is the Markov perfect equilibrium, and I'm going to concentrate on equilibriums in which expectation is a function of the current value of the state variable only, and not a function of I don't know, the whole history of the evolution of the state variable or past inflation or whatever. Okay, there are other equilibriums probably that satisfy that condition. Okay, and then I will briefly show you another solution in which we change the nominal debt for real debt, and the conclusion there is that it's actually going to be equal to the solution with commitment. Okay, so let's start with the solution for the model with commitment. Okay, we have rational expectations, so the expected inflation is going to be equal to the realized inflation. We write down the Hamiltonian here. I removed all the alphas and g's from the equations. Okay, so the traditional dynamic programming here work. Okay, we find the first order conditions. Okay. The first order condition for inflation. Okay. So this is going to be important. Here the central bank in the solution with commitment only tries to tax the monetary base. Okay. So by generating unexpected inflation, the central bank could tax all nominal liabilities, but under commitment, it behaves and it only taxes the monetary base. Okay, so we will see that that's going to change in the other equilibriums. Okay, so we have the first order condition for pi, and then we have the law of motion for the cost state variable lambda, which looks like a traditional growth model or a savings model. Okay, so lambda is the evolution of lambda is going to depend on the difference between the interest rate R and the discount rate rho. Okay, so if R is equal to rho, you actually get that debt is not going to change over time. If R is bigger than rho, you get that debt is going to be decreasing over time. Okay, so you do the traditional steps here that you do with these types of model. We economists, we get rid of lambda. Mathematicians like to keep lambda in place. So once we do that, okay, so there I have a typo. That should be x dot over here. That should be an x dot equals 2. Okay. The important thing here is that we get a system of two linear differential equations. Okay, so we can actually solve those by hand. So I'm very happy that I can do that. We can work out the solution for this system of differential equations and solve for the path of the inflation rate. So what we have here on the left-hand side of the equation is the tax revenue collected by the inflation tax, okay, pi times m, and that inflation tax is going to equal what the central bank spends on. And what does it spend? Well, it's going to spend in two things, okay? So if you look at this 2r minus rho, that's actually r plus r minus rho, okay? So it's going to pay interest on its debt. Okay, so here you have xt minus m. That's the interest-bearing part of the nominal liabilities for the central bank. Okay, so you pay interest on that debt, and you also pay an amortization on that debt, decreasing the real value of the debt over time. Okay, so that's what you pay out of capital. Okay, again, if r is equal to rho, then this term is 0, and you only pay the interest on that debt. Okay, so let me put some numbers here. Let's invent some numbers. Okay, so suppose that we have that xt minus m is equal to 1, or xt minus m is equal to m. Okay, so your nominal liabilities are 2 times the monetary base. Okay, then let's put r, I don't know, 5%, and let's put rho, I don't know, 4%. Okay, so how much inflation would we get here? Okay, so if we get 2r, that's 10% minus rho, that's 4%, that equals 6%. Okay, so if we start our economy with nominal liabilities that are equal to 2 times the monetary base, okay, then we would get that inflation would be 6%. Okay, if, I don't know, nominal liabilities are 3 times the monetary base, okay, then that number would double. Okay, so it would be 12%. Okay, those are not big numbers for inflation in Argentina, and of course we can get very high numbers by putting a lot of debt. Okay, but you have to put a lot of debt to get high inflation. So if the central bank can commit, then central bank debt is not really a very big problem. Okay, that would be my conclusion here. The problem is, well, what happens if it cannot commit? Then things are going to get a little bit bad. Okay, so let's look at the inflation targeting solution. Okay, so now we set up the expected inflation as a function of time only, and well, obviously the initial condition x0, but that's not going to change throughout the problem. Now we write down the Hamiltonian again. We keep the term expected inflation there because, well, the central bank doesn't really have to deliver that inflation. Okay? It's not the commitment solution, and we find the first order conditions. Okay? So now, important thing, the central bank tries to tax all nominal liabilities. Okay? In the solution with commitment, we had an M there instead of an X, and that meant that the central bank with commitment only tries to tax the monetary base. With an X there, then it's trying to tax all nominal liabilities. And well, if your monetary base, if your tax base is higher, you want to tax more, and that will lead to more inflation. Okay. The second order, the second equation, okay, the evolution for the constant lambda, now it's a little bit different, but once we impose the rational expectations conditions that pi e in equilibrium or in this quasi-equilibrium has to be equal to pi, then it's going to disappear and it's going to be the same as before. Now, we can do the same steps. So for the evolution of the inflation rate and the state variable xt, we get again a system of two differential equations. Now, the first equation, the evolution for pi, is not linear, so we are not going to be able to solve it with pen and paper, but we can still do the numerical simulation. Okay. The numerical simulations will show that even though it is not linear, it is very linear. Okay, so it's not going to be very different from the solution with commitment. Inflation is going to be a little bit higher, but it's not going to be that bad. Now, this one is the one that I'm more interested in, and it is the solution without commitment. Okay, so the central bank has no instrument that guarantee that it will fulfill its promises. Okay, so now we are going to work under the assumption that expected inflation is a function of the evolution of the state variable xt. So pi et is equal to f of xt. We write down the Hamiltonian. Okay, we put that function there, which the central bank takes as given. Okay, and we do the math. Okay, so we put we find the first order conditions. Again, we have that the central bank is trying to tax all nominal liabilities as before, but we have another effect, which is this one here. Okay, so that's the amount of debt that you have. Okay, so your liabilities x minus the money supply. Okay, so that's the interest-bearing part, your liabilities, multiplied by f prime. Okay, so how does the expected inflation rate change with the stock of nominal liabilities? Okay, so what the central bank here is saying is something like this. Okay, if I collect more inflation tax, I can pay down my debt, and that lower debt is going to affect expectations. Okay, and if I can lower expectations, then the nominal interest rate that I have to pay on my debt will be lower, and that gives the central bank an extra incentive to inflate away the debt. Okay? And that turns out that it's going to be very, very important. Okay. So what is an equilibrium in this setup? Sorry. So let big F of x and little f be the solution to the central bank problem. Okay, so imagine that you plug in a function little f, you solve the problem for the central bank. Okay, an equilibrium with rational expectation is defined as a policy function big F of x f that satisfies that big F of x f is equal to little f of x. Okay, so you plug in a function little f, you solve for a big function f. If what you get out of the solution is the same function that you plugged in, then you found an equilibrium. Okay. So one way that one could try to solve this problem is, well, let's plug in a function little f, solve, and see if what we get out is the same. If not, then let's try the new function, plug it in, and hope that it converges. Okay, so the usual mechanic solution. But turns out that we can actually use the implicit function theorem here to work out the algebra that is going to describe the solution, and then we can use the differential equations, simulate them, plug them into the computer, and solve them. Okay, so I'm going to use this implicit function theorem here. F prime equals to pi dot divided by x dot. Plug it there, and then solve for the equation. Okay. Turns out it works out pretty well. Okay, once I do that, then I get this differential equation for pi dot. Okay, I'm not going to read it out; it's a mess. Okay, so turns out that this equation, we can look at it in a slightly different way. Okay, we can put it like this, and it's going to summarize all three solutions which I presented so far in one equation. Okay. So if the second equation is just the evolution for the real value of nominal liabilities, that one is the same in all three solutions. But if we look at this term only, okay, and we forget about the first two factors, then that's the solution for, or the equation that describes the solution for the case with commitment. Okay, if we add the second factor, then that's the solution for the case that I called inflation targeting. Okay? And if I add this third term, then I get the solution, or the equation that describes the solution, I'm sorry, for the case with no commitment. Okay? The first one, it's a linear equation. The second one, I mentioned, well, it's not linear, but turns out that it is pretty linear, at least for reasonable values of nominal liabilities. But once we add the third factor there, then it becomes highly nonlinear. Sorry, and the reason is that we have a term there which is dividing. Okay, so we have this term there which is dividing there, and that term can go to 0, and that means that the whole thing is going to go to plus or minus infinity, and that will, well, make things really weird. Okay, so that term there is going to be important. Okay, so these three models have a common steady state, which is one in which there is no inflation, and nominal or nominal liabilities are equal to the monetary base. Okay, so there's no interest-bearing debt in the long run. Okay, and if we are close to that steady state, then they are all going to be pretty much the same. Okay, so that's going to be like saying, well, if we are close to the steady state, then the time inconsistency problem is not really a very big problem. Okay, whether you have commitment or not, the solutions are going to be very similar. But as we move further away from the steady state, the nonlinearity in the no commitment solution is going to start to kick in, and inflation will become very high, very rapid. Okay, so as I mentioned before, this has to do with that term that it's dividing on the law of motion for pi, for the inflation rate. The term is r times x minus m minus 2m minus x pi. Okay, so that's the term that is going to be troublesome, in particular when that term is equal to 0 or close to 0. Okay, so when is that term equals to 0? Well, that term is equal to 0 if pi is equal to whatever you have there. I'm not going to be reading that. That term is not really that important, but turns out that there is something important about that term, and it is that it has a vertical asymptote. Okay, so if we look at this equation on a plane, on a x pi plane, okay, there's a curve on that plane for which pi dot is equal to plus or minus infinity. Okay, and that curve again has a vertical asymptote, and that vertical asymptote turns out to be x equals to m. Okay? So what that implies is that the inflation rate is going to go to infinity, okay, or the initial inflation rate is going to go to plus infinity as the initial value of nominal, or sorry, as the initial value of liabilities, real liabilities or nominal liabilities, depending on how you want to look at it, is equal to 2 times the monetary base. Okay. So let me try to show you a graph, how that looks like. Okay, so this is the phase diagram for the solution with commitment. Okay. In this region here, above the red curve, okay, you get that you move in this direction, okay, and the green line, yellow, greenish line is the solution with commitment. Okay, so if you start here, you move along the saddle path towards the steady state. Okay, no magic there. But once we look at the solution without commitment, okay, we get a lot more curves to put on the phase diagram. There are many curves. I'm just going to look at this one here. Okay, the blue line. In the blue line, that would be a phase changing curve in the phase diagram. We usually have the x dot, pi dot curves, you know, in which you change direction. This one also is a curve that changes direction. But it's a very funny curve because it's not that it goes from positive to negative, like crossing 0. It goes from positive to negative, from minus infinity to plus infinity. Okay, so actually, if you get very close to this curve, like for example there, that red dot, okay, there you will be in a point in which inflation rate would be dropping dramatically. Okay, so the pi dot there would be very close to minus infinity. Okay, so now let's imagine that we solve these differential equations backwards. Okay, and we start very close to the steady state. Okay, we start there. Remove all these curves. So imagine we start there, very close to the steady state. Well, very close to the steady state, we move very similar to the solution with commitment. So it's kind of linear, okay, going this way. I'm going to be going along the purple line now. But imagine we try to keep on the green line. The green line, try to keep moving across along the green line. Then we would hit the curve. The pi dot equals to infinity. And we are actually on the minus infinity side. So actually you cannot get to the curve. You cannot cross this curve here, this light blue curve. Okay, so you actually have to start bending up. And since it has a vertical asymptote, when your solution will also have a vertical asymptote. Okay, you have to be moving northeast, but you cannot cross the 2m line. So, well, you have to go up. And going up means, well, your inflation rate has to go to infinity. Okay, so this is like working backwards in time, which means that if you start close to 2m, then, well, your saddle path will put you on a very high inflation rate. And then you move back down to the steady state. Okay, so that's that's how a very high inflation rate can come up with this type of model. Okay. Actually, what would be interesting to ask is, well, what happens if you have more debt? What happens if you start here? Well, actually, there's no equilibrium with rational expectations there. Okay, so you basically don't have a solution. Okay, so that would, in my view, that would be a hyperinflation. So what's going on? Okay, so there are two things going on in the solution without commitment. One is the standard argument that, well, if the central bank cannot commit, then every period is trying to tax all nominal liabilities instead of the monetary base. But with rational expectations, you don't do that in equilibrium because people anticipate that you will charge a very high tax on nominal assets, and they put that inflation tax as a surcharge on the nominal interest rate, and whatever you tax them ex post, you end up paying with higher nominal interest rates. Okay, so that's going on there, but that's also going on the inflation targeting solution which I showed, and there you don't get hyperinflations. Okay, so what else is going on? Well, there's another effect, and as I mentioned before, the central bank knows that by lowering the stock of debt, it will lower the inflation expectation. And by lowering inflation expectations, it can lower the interest rate, the nominal interest rate that it has to pay in the future. Okay, so it has an incentive to pay down the debt faster. If I pay my debt faster, inflation expectation falls. If inflation expectation falls, well, today I get to pay a lower interest rate, and that's good for me. Okay, so that extra incentive means more inflation. Of course, agents anticipate that effect with rational expectations, and you end up having an even higher inflation. Okay. So let me mention something else now. So when I presented the model, I told you that, well, I was going to work with a quadratic loss function to keep the algebra simple, but that assumption actually had effect on the solution. Okay, with a quadratic loss function, okay, the upper limit that you can get on nominal liabilities is twice the monetary base. Okay, so you can have as much debt as you have monetary base, add the two of them, and you get 2 times the monetary base. But turns out that two times the monetary base is exactly the 2 from the quadratic loss function. Okay, if we work out with a more general loss function in which we have a curvature on the loss function that is governed by a parameter theta, then that theta is going to be the upper limit. Okay, so in general, the upper limit is going to be x equals to theta m. So what that does mean? Well, it means that more inflation-averse central bankers will be able to sustain higher levels of debt, even without commitment, and deliver a lower inflation in that sense. Okay, so let's go for a inflation-averse central bank. Okay, so now I'm going to show you some simulations. I'm going to show you the continuous time simulations and then the discrete time simulations. And as I mentioned before, there's a time period length effect here, okay, which I don't know, I've never seen it before. So it's something that it's worth looking further into. Okay? So the solution is going to depend on the period length. Okay, so nobody, I don't know, if you think about a growth model, okay, and you calibrate the model and you calibrate it to be yearly or quarterly, you adjust the parameter values and the solutions are basically the same once you, I don't know, analyze the quarterly model. Okay? So here it doesn't work that way. The solution is going to be different whether you work with a yearly model, quarterly model, monthly, weekly, or daily. Okay. let me present those simulations now. Well, I'm gonna choose two parameter models: are the interest rate equal to 5%, the discount rate equal to 1%. These are just like random parameters, nothing in particular there. I'm gonna show you the solution for the continuous time model, and then I'm gonna show you the solution for the discrete time model in a yearly frequency, monthly, weekly, and daily. Okay, so yearly is going to be frequency 1, monthly frequency 12, weekly 52, daily 365. Okay, so now here we have the continuous time case. Okay, so these are the policy functions for the three solutions which I presented so far. The commitment is the blue line. Okay, so it's a straight line, linear solution. Okay, so in this case, if you have nominal liabilities, which are 3 times the monetary base, then you get an inflation rate that it's a little bit higher than 15%. Okay, so nothing to worry about, nothing compared to what we had in Argentina. Okay, the solution with inflation targeting, which is the yellow line, well, you get somewhat higher inflation, but not that much. And it's also pretty linear. Okay, so there's some curvature on that function there, but it's barely noticeable here. Okay, and in this case, for nominal liabilities equals to 3 times the monetary base, you get 25%. That's a regular number for us. Okay, now when you look at the solution with no commitment, that's the red line. Well, you see that that goes up very fast. Okay, so they're very similar here, when you are close to the steady state, but as you move further away from the steady state, then inflation starts to pick up very, very fast. Okay, and there's the vertical asymptote at 2 that I mentioned before. Okay, so it's not really converging there on the graph. They don't get very close, but that's because, well, if I wanted them to be very close, I would have to put like very high numbers on this axis, and you wouldn't be able to see those other solutions. Okay, but there's the vertical asymptote is there. Okay, so now let's see what the discrete time solution to the model looks like, the simulations, and if I'm correct, this should be a yearly basis. Okay, so now do the Bellman equation stuff that we do for these types of dynamic problems. Okay, solve it. The solution with commitment is basically the same as before. The solution without commitment in the inflation targeting case, the yellow line, well, it's there, it's a little bit higher. There's not much going on there too. And if you look at the solution without commitment, okay, the one that in the continuous time case had a vertical asymptote, well, here there's no vertical asymptote, and it's pretty linear, a little bit of curvature, but not much. Okay, so you get that if you have 3 times the monetary base as nominal liabilities, well, you get like 30% inflation. Okay, that's low. Now let's go to a monthly frequency instead of a yearly frequency. Okay, so no change basically on the commitment and the inflation targeting solutions. Okay, but you already see that the no commitment solution starts to get away. Like it starts to deliver a lot more inflation. Okay, you don't get the vertical asymptote at 2. Okay, so you see that you can cross the 2 there without any problem. Okay, but you already start to get much higher inflation. Now let's go to a weekly frequency. Okay, again, no change whatsoever on the commitment and inflation targeting solutions, and you already get the vertical asymptote. There's really no vertical asymptote. Okay, on the discrete time, you can go to whatever value you want here. Okay, so you will always find an equilibrium in this case, but it starts to look a lot like the continuous time case. Okay, and even more if you put the daily frequency. Okay. So this frequency is something that I don't know, I haven't noticed before on the literature on how I don't know, time inconsistency or time consistent policies work with changes in the frequency. Okay, let me skip this one. That's for the discrete time. These are the paths for inflation over time. Okay, for different levels of initial nominal liabilities. Okay, so here you have nominal liabilities equal to 1.75 of the monetary base. Okay, so debt is 75. Initial debt is 75% of the monetary base. There's really not much inflation to start. Okay, so independently of the frequency, you start with 25, 20% inflation. As you start increasing the level of debt, okay, inflation starts to get a lot higher. Okay, so here with 2.25, these are the discrete case solutions. 2.25, so nominal liabilities are a little bit over 2 times the monetary base. You already get a very high inflation rate if you start to work with very high frequencies. Okay, and the numbers keep getting higher as you put more debt into the model. Okay. Okay, so this table here, I want to show something. Okay, so all right, maybe the initial inflation rate is very high, but it's for a very brief period of time. Okay, so if you do the daily model, then that initial inflation that I'm showing is just for 1 day. Okay, so maybe inflation drops very fast, and over a year you don't get a lot of inflation. Okay, or a lot more inflation. So here, this table shows the accumulated inflation during the first year, okay, for different frequencies and different initial levels of debt. Okay, so in the model in which the time length is 1 year, so that means that the central bank reoptimizes once a year. Okay, even with a very high level of debt, 3. Okay, so debt is 2 times the monetary base. Inflation rate there starts at 33% in the first year. Okay, but if you go to the daily frequency, the inflation rate during the first year is 230%. Okay, so the numbers are a lot different. Okay, so the time period matters. Okay. So why does the period length matter? Okay, so I really don't have a very good explanation that I'm certain, but I was discussing this issue with Fernando Alvarez, and he gave me some intuition to it. So I'm pretty sure that it has to be right, given that it comes from Fernando. So this is not my idea, or at least this is my interpretation of what Fernando was trying to tell me. Okay, so think of the discrete time version of the model, okay, as a continuous model in which the central bank is forced to make decisions for a discrete chunk of time. Okay, and once that decision is made, okay, so I choose my first period inflation rate and my period is 1 year, then I'm basically fixing the inflation rate for a whole period in which I could reoptimize. Okay, that's like commitment. Okay, so if you have a discrete time model in which the central bank chooses variable for 1 year, that's like saying that the central bank can commit for 1 year. Then you get your next chance to reoptimize, and then you recommit for 1 more year. Okay? And well, that's like adding a lot of commitment to the solution. Okay? So the idea is that a model in which the period is very, very long the solution without commitment, well, it has to look a lot more like the solution with commitment. Okay, and as the time period gets shorter, okay, that ability to commit disappears, or well, you are committing for shorter periods of time, and the time inconsistency problem then it's going to get bigger. Okay, so that's why these solutions kind of like look different according to the time period. So again, if the intuition is right, then it's all Fernando's. How to say? It's all Fernando's merit, okay, not mine. So last issue here. I mentioned before that I was gonna discuss 4 solutions. I presented 3 solutions so far. The last solution is okay. So let's change the nominal debt for real debt. Okay, this looks a lot like the Plan Bonex for those that are familiar with Argentine history. Okay, so let me go back to the beginning. Okay, so here we had the evolution of debt on the central bank. This was all nominal debt. That's what I'm arguing was the cause of the quasi-fiscal deficit. In the early 90s, okay, Argentina basically swapped all that debt, all that nominal debt for real debt. That was the Plan Bonex. Okay, so the idea was that people put their money in the bank, okay, as a time deposit, certificate of deposit. Then the bank gave the money to the central bank, and the central bank paid interest to the bank, and then the bank used those interests to pay back the interest on the private sector that had made the original deposit. Okay. The Plan Bonex consisted on, okay, let's give a Bonex bond, okay, which is a dollar-denominated bond, to the people who made the original deposit. Okay, so if you had a $100,000 certificate, or in pesos, no, equivalent to $100,000 in pesos deposited in a bank, then they gave you $100,000 of Bonex bond. Okay. That swap, it changed the real value of or changed the debt from nominal to real. Okay. And turns out that if you change the debt from nominal to real, okay, so instead of having big D nominal debt, we have little d real debt. Okay, then the liabilities for the central bank are P times little d plus M. Okay, the interest payments are R little r times P times little d. Okay, and those have to be financed with money creation or issuing more real debt. Okay, turns out that if you do this, you do the math, and you work out for the budget constraint for the central bank, you get the same budget constraint as in the case without commitment. I'm sorry, as in the case with commitment. Okay, so the solution in which you have real debt is exactly the same as the solution in which you have commitment. Okay, so basically the central bank is not trying to tax all nominal liabilities, it's only going to be taxing the monetary base, because, well, you cannot tax with inflation real debt. Okay, so whatever you try to tax it is going to go up in the value of the debt. So in this scenario, swapping real debt for nominal debt might be a good idea. Okay, so if you cannot commit issuing debt in real terms, well, that's not something really new, but here we get another application of that principle. Okay, so summing up all the conclusions from what I've shown you. Okay, if the central bank can commit, then nominal debt is not a very big problem. Okay, I've shown you simulations in which, well, you get pretty decent numbers of debt. So imagine here in Argentina and in many countries, the monetary base is like 10% of GDP. Okay, So if you have debt, which is, I don't know, 2 times the monetary base, that means that your central bank debt would be 20% of GDP. That's a pretty big debt, but turns out that it's not going to generate a lot of inflation. Okay, so it's not going to be a big problem if the central bank can commit. Okay, but if the central bank has no credibility, then, well, we've shown that that can lead to very high levels of inflation, even for reasonable levels of debt. Okay, I don't know, debts that are 10 to 20 to 30% of GDP. It's not unusual to see countries right now having central banks that have debt that are much higher than those numbers. Okay, again, these results were obtained with a money demand that is perfectly inelastic, so there's really no Laffer curve effect. We could add that. We'll discuss that later. And also, well, that real debt is a good way out if you cannot commit, if you have no credibility, and you have a big stock of debt to pay in the central bank, then let's change it to real debt. That might be a good idea. Okay. So further extensions that one can imagine adding to this model, some of them I've tried, some not. The elastic money demand, that's actually pretty easy to put into the model. Okay, so it's just adding some more lines of code to the MATLAB programs. Okay, but what we get is pretty reasonable. Okay, if we have an elastic money demand that is going to generate a Laffer curve effect, okay, then the upper limit on debt is going to be smaller. Okay, that's not something unexpected. Okay, and that can actually help to understand, well, why we get much higher levels of inflation than those predicted by the simulations that I've shown. Okay, so then other extensions that one can add, well, in this setup, in this model that I presented, only realized inflation matters for the central bank loss function. Okay, there's no distinction in the loss function between realized and expected inflation. Okay, one can add both to the loss function. Okay, make a loss function that depends on realized and expected inflation. And again, what we get is that we add expected inflation to the loss function. Okay, then the upper limit on debt is also going to be small. Okay, so let me go back a couple of slides to the loss function. I'll show you what I mean. Okay, so one could add something that looks like very similar to this. Okay, but with PE, the theta over theta there. Okay, and let's add, I don't know, a delta here multiplying and a 1 minus delta here. Okay, so their delta would regulate, okay, what's more important, realized or expected inflation. Okay, I'm working in this case with the case where delta is equal to 1, but one could add this. Okay, and well, higher delta, meaning like only expected inflation matters, is gonna make things worse. Okay, so if only expected inflation matters, then what you want to do is to inflate all the debt away immediately. Okay, because, well, period zero, that debt is given, and inflation is unexpected. You take expectations there at period zero as given, and then just inflate away the debt. That's usually what you get in these models, where only expected inflation matters. Well, it turns out that in this, if we do this type of modification, well, there's a value of delta, which for the quadratic case is equal to 1/2. So if you care equally among expected and realized inflation, okay, then the upper limit on debt is 0. Okay. That's something else. Other things that one can do is, well, abandon the ad hoc loss function for the central bank, add a household sector, get an endogenous money demand, and work out the benevolent central bank solution, okay, the one that maximizes household utility. I've been doing some of that work with the Nicolini's model. Okay, I get some results which are very similar to what we have here under particular specifications of the model. In particular, it is interesting that the result that the inflation rate depends on the period length, that holds there too. Okay. And the last extension that one can add to the model is, let's add real assets to the problem. Okay, so let's add real assets. Okay, so let's add, I know, international reserves to the balance sheet on the central bank and see how the problem works out there. Of course, well, one would have to make some assumptions there. For example, that the interest that the central bank can collect on international reserves are smaller or lower than what you have to pay on your nominal debt. Okay, at least in real terms ex ante. Of course, the central bank can always devalue and get a very high ex post nominal rate of return on those real assets. And then what is more critical is, well, we need to have a good reason on why the central bank wants to have real assets. Okay. But turns out, well, we can ad hoc, we can do it. Okay, let's just add a utility for the central bank that depends on those real assets. But then it's more important also to think, okay, what are the fundamentals behind that gain that the central bank has? Okay? So maybe that the real rate that you have to pay on your nominal liabilities is a function of the real assets or something like that. Okay, but that's something that I still have to explore further. Right, guys. I think I'm pretty much done, and that's the last slide. So if anybody has questions, now this is a good moment to do them. Yeah, Francisco, go ahead. Oh, I'm sorry, I was reading only the first line of your question, and I was waiting. In your solution, the central bank always wants to reduce the stock of debt. Yes and no. Okay, so in the commitment solution, the fact that it wants to reduce the stock of debt or keep it constant depends on the difference between R and rho. Okay, so if R is equal to rho, then the commitment solution would be one with constant real debt, or debt constant in real terms, I'm sorry. In the other solutions, then yes, it would want to lower the stock of debt, even if R is equal to rho. Okay, so that's that's the same thing I've seen in a paper by B.B. Chari on financial repression that he presented in the Lucas conference in the BFI. I think it was 2016. Yes, 2016. Okay. So the idea here is that the solution with no commitment, that incentive to okay, so yeah, I'd look briefly at that paper. So whatever I say, it should be taken with extreme care. Okay, so the Manueli paper is a model in which the real interest rate is determined endogenously. Okay, so there, yes, if I had to guess, then R would be equal to rho. No, the real interest rate would be equal to rho in the commitment solution, and then yes, you would want to keep the real value of that constant. Okay, so let me go back one more minute to this. Okay, so these are the first order conditions for the solution without commitment. Okay, oops. I don't know how to clear everything, but let me see. Oops. No, there are too many options. I'm not gonna try to remove all the things that I've drawn here. But if you look at the lambda dot equation, okay, you will notice that you have on the second term on the right hand side, you have r plus x minus n times f prime x. Okay, so f prime x is how much the expected inflation rate changes as a function of the stock of nominal liability. Okay, so the idea is, even though here I'm just working with any general function that the central bank takes as given, what is reasonable to assume first is that, well, expected inflation should be an increasing function of the stock of nominal liabilities. Okay, so if you have more debt, then that means you will have to collect more inflation tax, well, more taxes, whatever. So that f prime should be positive. And again, we are working in a situation, we are thinking of a situation in which the central bank has debt. Okay, so that means that x is bigger than n. Okay, so you get this x minus n, which is positive, times f prime, which is positive, you get a positive term. So even if r is equal to rho, okay, the evolution of lambda is one that is equivalent to one in which you have a higher real interest rate. Okay, even if the actual interest rate is equal to the discount rate. So you end up wanting to pay down the real debt, even if the interest rate is equal to the discount rate. Okay, and again, this is the same result that B.B. Chari gets in that financial repression paper. It's a discrete time version of the model. It's all mostly simulations, but he gets to that same result. And my intuition is that what's going on is this thing here. Okay? And it has to do with the fact, again, that the central bank is when it is optimizing, it is taking into account the fact that the change in the stock of nominal liabilities will have on expected inflation. Okay? And well, again, if I can lower expected inflation by lowering my stock of debt, then that gives me another incentive to lower my stock of debt.
Okay, thank you, Alejandro. So if there are no further questions, then we conclude the seminar. Thank you, Alejandro. It was very interesting. And hopefully to see you all again next week for our next webinar.